on, even for the stars. And we're probably going to hear some about that tonight from our speaker, Tim Thompson. Tim is a prominent figure in Southern California astronomy, both amateur and professional. He's a friend of the club. He's spoken to us many times. He always gives us an interesting talk. And he was kind enough to jump into the gap when our planned speaker came downhill. So without further ado, Tim Thompson.
So there it is, the universe of stars. I'm going to talk about stellar evolution, stars, stellar structure, and a whole bunch of stuff to do with stars. Because it's stars, it's astronomy. If there are no stars, it's really boring, right? So, well, okay, for you planetary people, I'm sorry I said that, but you know how it is. Do I change this? Can I push the button? If I push this button, which button do I push?
There, this one.
This one. Oh, hey, there we go. So let's start with what is a star anyway? So here we have planets, anything up to about 13 Jupiter masses counts as a planet. Generically, according to the IAU definition, you're not a planet if you're not going around the sun, but we can skip that for a minute because according to the IAU definition, Earth is not a planet, but we'll get around to that later if you want to. But the internal heat comes from heat left over from the formation of the planet and from nuclear fission, the radioactive decay of isotopes in the mantle and the core, mostly potassium, uranium, and a bunch of other stuff like that. Get up to between, say, 13 and 8 masses, and now you're into what's left over of the brown dwarf, and from deuterium fusion. Deuteron is a proton with a neutron attached to it, and hydrogen with the extra protons called deuterium. If you hit it with a proton, it's pretty easy to make that fuse, and so you get deuterium fusion, a very low energy release reaction in brown dwarfs that keeps them warm for a very, very long time. That requires an internal temperature around 3 million kelvins. For a star, it has to be a minimum tiny mass star would be about 80 Jupiter masses, and that's 8% of the solar mass, so it's really quite small compared to the sun. And now you get proton fusion, which is smashing a couple of protons together, and eventually you wind up with helium, and I'll explain that all later on. That requires a minimum temperature about 5 million kelvins or 9 billion Fahrenheit. So anything that does proton fusion is a star. If it's only doing deuteron fusion, it's a brown dwarf. And if it's a wimpy little thing like the Earth, Jupiter, you know, it's a planet, but you can get quite big. So at least that's what a star is. Yeah.
Come on.
We are attempting. Eventually, the slides do push forward. When you push the forward button, it just takes a few minutes. I mentioned this, I'm sure, at the last talk I gave on Hubble's constant. So I won't go into it in great detail now. Cosmological distance scales, astronomical unit, typical solar system scale, parsec was originally 1 arcsecond of parallax angle, but the IAU redefined it in 2015, I think it is. So now it's that many, exactly 648,000 over pi astronomical units, which turns out to like 19 trillion miles. And it turns out that if you compare the old parsec to the new parsec, they are different from each other by approximately 300 miles. And that's 300 miles out of 19 trillion miles. So you're not going to measure this, no matter how hard you try. But I have given the numbers to ridiculous precision because they're all definitions of exact numbers. Every number in the definition is exact. Therefore, it has infinite decimal precision. Therefore, you can carry out the decimal points as far as you like. And I have, just to show how pedantic and ridiculous I can be. And if you click to the next slide, I mentioned this too, and I'll mention it again just because I think it's kind of cool. If you adopt a scale where of 1 inch per astronomical unit on your scale model, 1 mile is now a light year. So if you want to say I'm by the Andromeda Galaxy, which we'll talk about, is 2.5 million light years away. It will be 2.5 million miles away on your scale model. So if you wanted to build a scale model of the universe with this 1 inch per AU scale, you would have to put the Andromeda Galaxy 2.5 million miles away on your scale model, which is 10 times farther than the apogee distance of the moon from the Earth. So your scale model will be very large. So if you want to build a scale model of the universe you can put on the floor in this room, you need a much smaller scale than 1 inch per AU, or never. Okay. So first thing I want to talk about is obvious star is the sun. You're going to talk about stars. The sun is the only star we can see up close and personal, but not too up close. You'll burn a hole through the back of your head and the red light will shine through it. It's a bad idea. So here's the sun. Here are the vital statistics for the sun. You know, I like to point out that the core temperature is about 28 million degrees Fahrenheit. If you go outside and you look at the sun, don't do it because it's a bad idea. It burns a hole in your retina, you know, and it's really dumb. But you know, some people, famous people, do it. And so if you look directly at the sun, you will see the photosphere, which is about 9,800 degrees Fahrenheit. Down in the core, it's about 28 million Fahrenheit. A trillion Earth atmosphere. That means a pressure of 1.4 trillion pounds per like square inch, 14 trillion pounds per square inch, actually. So that's why we don't send probes to the core of the sun. We send the Parker Solar Probe to probe the solar corona, but we don't send probes because if you're an engineer and you can design a spacecraft that will withstand these conditions, you will invent a brand new Nobel Prize in engineering just for you. It would be really tough to be able to do that. But I do want to draw your attention to something which I will show you on the next slide. Big deal number one. So if you fall asleep during the presentation or you can't remember anything, this is one of the things you must remember. The sun is bigger than 95% of the other stars. It is standard practice to say that the sun is an average star. Everybody says it. Neil deGrasse Tyson says it, and he's really famous. It's not. The sun is not an average star. Nothing that's bigger than 95% of everything else is average. They call it average for various reasons that are not really very good. And I'll probably mention them later anyway. But remember this, if you forget everything else, take home with you that the sun is a very big star, which means you don't have to have an inferiority complex because you come from some average, ordinary star. No, the big star, so we can go out there into the universe and say we came from a big star. So here is what that background image looks like. And there is the Earth in true size comparison. So that is indeed how big the sun is compared to the Earth. So that if the sun were a planet, it would be a very big one. The structure you see here, there's a hydrogen alpha image, and I know some of you are experienced hydrogen alpha solar telescope observers. The structure comes from magnetic fields, and we'll see how that structure arises in just a minute. This thing up here in the upper left, that broad white band, the long band, if you could see it from the side, it would be an arcade stretched out over the surface of the sun like this, a loop, like loop prominence that comes out. You can see, can't see it from the side because you're looking down on it, but you can sort of see the side of it. On the bottom side, there's some things sticking up. So, and you see prominences along the edge of the sun. Okay, next. So those dark things are called sunspots. This image is about 100,000 miles long. There's the Earth by comparison. As you can see, the spots can be quite large, bigger than the Earth. It's a magnetic structure. So think of it, well, incorrectly, but think of it anyway, as like a bubble of magnetism that sticks up out of the surface of the sun. the magnetic field acts like a Star Trek style deflector. It will not allow charged particles to pass through it. It's a barrier that inhibits and prevents convection, physical motion of hot gas into the volume protected by the magnetic field, which means only radiative heat can get in, which means the interior structure of the sunspot cools to a lower equilibrium temperature than the sun around it. Now, if you took a piece of this stuff and put it here, it'd be white hot, incredibly thousands and thousands of degrees. It only looks dark by contrast, because this is only like 5,000 degrees, maybe 6,000 degrees. This is 10,000 degrees. So it's a lot brighter and it looks darker, but it would not be darker. So the fact that these are cool areas was proven at Mount Wilson Observatory in 1908. Before that, actually, I'm sure, by George Ellery Hale using the Snow Solar Telescope in Mount Wilson by doing spectroscopy in the early days of astrophysics, which was basically invented at Mount Wilson Observatory, which is an obvious overstatement because it wasn't, but I said so anyway, because I've been there for so long. It's Mount Wilson Observatory, and that's what you say. That's the way we think. You see these bright spots, that's where the hot gas comes up. And then the cold, the dark lines in between them is where the cold gas, and it's convection cells, just like you get in Earth's atmosphere doing this. And you can see, looking at the Earth and comparing the convection cell size, they're about the size of Texas, a little bigger, a little smaller, somewhere the size of the US. So this is what sunspots in this part of, in the convection cells, there's a bunch of stuff going on in the surface of the sun, and most other stars especially. This is what creates the magnetic structure. These images coming from the Transition Region and Coronal Explorer in 1999. This is the same image, positive image on the right, negative image on the left. So they tell you, if you see different things, I think you can see more detail, and the projector is not projecting the image with the kind of resolution you'd see on your computer screen. So these images look a lot better than they appear in this projection, but you can see a lot of small magnetic line details in the negative image that don't show up as well in the positive image. This is what creates that wiggly structure that I showed you in the hydrogen alpha image of the sun. It's a lot of stuff like this. And it's from this region along the base of these loops that you get the corona and the solar wind launch away from the sun and fly out into the solar system to crash into planetary magnetic fields and that kind of good stuff. And it's a little harder to see in this image than it would be if projected on your computer screen, but you see the very delicate linear type structure in these magnetic fields, where the plasma appears to be like glued to a very small looping curve. Magnetic field lines are a mathematical device invented by Michael Faraday and perfected by James Clerk Maxwell, and they are purely mathematical. However, if you look at a real plasma in a real magnetic field, that sure does look like the magnetic field lines that we use mathematically to describe them, have some kind of physical reality because you can see it in the structure of the plasma with your own eyes. I always think of that as being a fascinating aspect of plasma physics. So when you think about the corona being launched, here it is. This is a total solar eclipse in Rexburg, Idaho in 2017. If you have never been to a total solar eclipse, I have a question for you. Why not? And then I have a statement for you. What's holding you back? Go. It's not something you see. It's something that you experience, especially when you do it in August in Idaho, which is not famous for being cold. And during the total eclipse, the temperature drops about 20 degrees and you put on your sweater. And you don't normally do that. But it's a thing you experience, and it's really fascinating. this is a picture by David Pinsky that really presents the corona the way you would see it with your own eyes. A lot of people photograph these with ridiculous exposures, and the photographs and images show you lots of things you'd never see with your eyes. But this shows you what it looks like pretty much by eye. And you see a little prominence sticking out there. And the darkest thing you've ever seen, the most black thing you will ever see in your life, is this disk of the moon, because of the extreme contrast between this and the very bright corona. The one thing that you don't see in this image is the contrast between the moon and the corona is much greater than it appears to be in this image. So there's the corona flying out away from the sun, and it flies across space. Fortunately for us, the Earth is not actually that close to the sun, or we would not have nighttime, really. And if one of these things, if a big coronal mass ejection like that was actually pointing at the Earth and hit the Earth head on, you'd probably see aurora borealis in Mexico City or farther south. I know it's been seen in Mexico City before. You knock out all kinds of satellites, but most importantly, you would knock out the GPS satellites. And the reason that's really important is because I know some of you were old enough to remember the things we used to use called maps, which nobody has a clue what they are anymore. They just get lost. If they don't have GPS to tell them where to go, they just sit there and stare down the road and can't go anywhere and do anything. So without GPS, all society would just come to a screeching halt. And of course, you could overpower grids. In 1859, the Carrington event was that 1859, about the right date, I can't remember exactly, 1850. The Carrington event, that actually happened. Only in 1850s, the only thing we had that was kind of like that was the telegraph system. And the coronal mass ejection, the magnetic field embedded in the solar wind pushes the Earth's magnetic field, which moves through the conducting lines of the telegraph and generates electric current. And so it powered up the telegraph system without anybody ever turning on the switch. You just powered it up. And you could send messages without turning anything on. It also lit telegraph poles on fire and just did all kinds of things. And so you can overpower a global power network like that. And that did happen in northeastern Canada. I think it's back in the 70s, around 1980 maybe. But their power grid was knocked out by a solar coronal mass ejection. That kind of thing can happen. And those of you who lost power during the recent fires, that was me included, know how inconvenient it can be to be without electricity. And our great grandparents did just fine without it, but we aren't our great grandparents.
They didn't have all electric kitchens.
Yeah, that's right. So this is what the sun and a lot of stars look like outside. Now we're going to go look at the inside. Okay, the inside of the sun. Well, okay, there's the photosphere. That's the part that you would see with your eyeball if you were foolish enough to look at the sun without proper protection. What you do is you tell middle school boys, this works best for middle school age boys, that if you look at the sun through an improperly filtered telescope, no filter, your eyeball will explode. So you would think that would instill in them some respect. But no, they will go and get their buddies. Hey, Bill, come and look through this telescope at the sun. They are so desperate to see exploding eyeballs, they'll do anything because that's what they want to see. So it comes in handy when you're educating the younger set. But the density here, you have to go up 50 miles in Earth's atmosphere to find something sparse enough to match the density of the photosphere. So there's not much stuff there. And even if you go down to the bottom of the convective zone, that's where gas moves energy by physical convection. Still, the the density is somewhat less than the density of water. So this outer layers of the sun are pretty sparse. You don't get down to the density of water until you're inside what's called the radiant zone. In here, the temperature gradient is so extreme, you can't move energy by physically moving the gas. It just plows by radiation through the gas. And at the base of this convection zone, then you start getting convective currents. So the sun, when it rotates differentially. The equator rotates faster than the poles because of this. But down inside, it does not. This part of the sun rotates as a solid body. So there's a discontinuity here. And that's in most, all except the very hottest stars, the internal structure is just like this. And all the way down to the core here, you get your 14.7 trillion pounds per square inch. Okay. So what about those nuclear reactions? I could give you an entire hour-long talk about nuclear reactions in stars, and you probably don't want a course in nuclear physics. And so I'll just talk about this nuclear reaction and leave it at that. There's a whole bunch of nuclear reactions going on all at once, but this proton-proton reaction provides 85% of the sun's output power. So this is the one I'll talk about. Basically, you have a couple of protons and you bash them together. And if you're really lucky, they'll stick together for a very small amount of time and give you a helium-2 nucleus because it's two protons. Then it will fall apart because they don't like each other. And then very small fraction of the time, one of the two protons will throw away a positron. You get a deuteron and a proton. This is the deuterium fusion reaction, which I said powers brown dwarfs. They don't do this. They just do whatever they've got laying around in the form of deuterium. It fuses with proton and you get this. Helium-3, you get a couple of helium-3s together, throw away a couple of protons and you get this. Now, this is a very slow reaction. And this is a very fast reaction. So as you can see, it's going to be a lot easier to do this than it is to do that. This other chain reaction, this is responsible for about 2% of the energy in the sun, but in a higher mass star, this is actually important. It's basically a catalytic reaction. You start with carbon-12, hit it with a proton, you get nitrogen-13, it's unstable, radioactively decays to carbon-13, throwing away a proton. Carbon-13 is stable, hit it with a proton, you get nitrogen-14, that's stable, hit it with a proton. You get oxygen-15, not stable, throws away another positron, becomes nitrogen-15, hit it with a proton. It spits out a helium atom, a helium nucleus, and you get carbon-12 again, which is what you started with in the first place. This is an important reaction in hotter, more massive stars than the sun, but not so much in the sun. But this does lead us to big deal number 2. So there are a couple of really important things to think about here. Look at this reaction rate. An average proton running around in the sun, just minding its own business, bashing another proton, will have to do that for 8 billion years before it hits another proton hard enough to go through this, to actually throw away a positron, become one of these, and start the reaction. So it's a very slow reaction, even at 28 million degrees Fahrenheit. The sun is about 4.5 billion years old. The Cambrian explosion was about 500 million years ago, and that's where multi-cell life first shows up. So we only have one datum point, datum being the singular form of data, which you might not have known because nobody ever uses that word, but that's the correct English. One datum point doesn't tell you a whole lot if you're trying to make a statistical argument, but it took 4.5 billion years for us to show up. And the reason the sun lasted that long is this reaction rate. Speed up that reaction rate just a little bit, the sun lasts 2 billion years and we don't show up, right? So you need this in order for us to be here. And you notice this is a very fast reaction. This is 240,000 years on average, but that's 0.0003% of 8 billion. So basically, these two reactions are instantaneous compared to this one. That's the bottleneck. This is the one that holds everything up. The other point is it's very common. Remember, I said it's very common for people to say the sun's an average star. It's not. It's very common, almost universal for everybody to say the stars are powered by nuclear reaction. The sun is powered by nuclear fusion. Everybody always says that. It's completely wrong. Stop saying it. Correct anybody who does say it. They always say it because they're lazy. And they don't want to have to explain to you what's actually going on. So they just tell you the stars are powered by nuclear reactions, go away. Now you know something about stars. You don't. What's actually happening is that the star forms by the collapse of some big, humongous cloud of gas, mostly. If it's got dust in it, it's going to become gas. And as it collapses under the pull of gravity, it gets hotter inside. Remember, this requires a minimum of 5 million Kelvin in order to operate at all. So it gets hotter and hotter and hotter inside, and as you heat something up, it generates what's called thermal emission or black body radiation. Electromagnetic radiation is a function of the temperature alone, and that radiation is flowing out as gravity pulls in. So it resists the collapse. Likewise, mechanical pressure, it's hot. The stuff is moving around real fast, backing and either pushing out. But those two effects, black body radiation and mechanical pressure, are not enough. The star continues to collapse anyway. It gets hotter and hotter and hotter. Eventually, it gets hot enough to do this. And now something new is happening. First, these reactions emit high energy gamma rays, and these positrons are going to bash into electrons really fast and annihilate because they're antimatter. They're going to annihilate with the matter electrons and generate 511 keV typical matter-antimatter annihilation line for electrons and positrons. Now you have a whole bunch of extra high energy electromagnetic photons going out, and that's enough. That stops the contraction, and the star stabilizes and holds a high temperature like this, which allows these reactions to go on. So the nuclear reactions do not power the star, they stabilize the star by stopping the contraction. It's gravity that powers the star, because if this pushes the star out a little bit, it cools off, this reaction slows down or even shuts off. Gravity pulls it in again, it heats up again, it stops again because of this, and then maybe it does this again. So it's maybe pulsating a little micro pulsation that nobody cares about that much. So every star is a variable star, but it can't collapse because of this energy. So it's gravity that powers the star, and nuclear reactions don't power the star, they stabilize the star. That's physically what's happening. And then, as you can tell already, because you're bored stiff, it takes way too long to explain that to anybody. And so they just tell you, yes, powered by nuclear reactions, go away. So now that's big deal number 2. So the next time some famous person tells you that stars are powered by nuclear reactions, tell them, no, Dumbledore told you that they are not powered by nuclear reactions. Okay, so Okay, so now that we've talked about the sun and nuclear reactions, let's just kind of talk about stars a little bit. If it were not cloudy outside, and I think it's still cloudy, it was when I came in, you could go outside, look up, and see that, because it's in the sky tonight. The Pleiades open cluster, right? So this dust, despite rumors to the contrary, is not dust left over from the formation of the stars. It's just a dust cloud that's going this way, and the stars are going that way, and they're strangers passing in the night, and eventually they will be divorced from each other. So look at these bright stars and assume they're out here somewhere floating in this kind of globular thing. And way back in the background, these little things, these are distant stars way far away. So there's depth in the picture, even if it's not a 3D image projected. It's called an open cluster because there's a lot of room between the stars. You can see maybe 500, maybe 1,000 stars. 450 light years or so away, 454 light years, I got it right there. If you look it up on Wikipedia, it will tell you it's 16 light years across. So you can look at this thing for yourself and say, across this way, that way, that way, what does that mean? I don't know what it means, neither does anybody else. But if you got to draw a picture around it, you kind of go, okay, something about 16 light years across. Nobody knows what, but about that big, a few hundred stars. And they're mostly open clusters or dominated by young blue stars that are very high temperature compared to the sun. But there's another kind of cluster. This is a globular cluster. Omega Centauri is the largest of the globular clusters in the Milky Way. There appear to be basically two kinds of globular clusters. This is the big kind. It's the biggest of them all for the Milky Way. It's not the biggest in the local group. I think that's the cluster around M31G1, the biggest in the local group. So the Pleiades had 500, maybe 1,000 stars. There's probably 10 million stars here. And evidence for multiple episodes of star formation. This is probably the remnant core of a dwarf galaxy that was gobbled up by the Milky Way. Galaxies like the Milky Way get big by eating smaller galaxies. And the Milky Way is very big galaxy, much bigger than more than 95% of the other galaxies. Just like the sun is a very big star, Milky Way is a very big galaxy. You've got nothing to feel inferior about. Big planet, big star, big galaxy, you're in good shape. So you can see there's not a lot of room between stars here, but almost every line of sight is hitting a star, which was not the case for Pleiades. So if we zoom in, this is a Hubble Space Telescope picture of the core of the Omega Centauri cluster. There are 50,000 stars in this image. I do not count them, but the people from the Hubble Space Telescope say that's how many there are, and I will take their word for it. If you want to start counting dots, be my guest, but I don't think we'll keep the slide up long enough for you to accomplish that task. But as you can see, if there are not 50,000, there are a lot. That certainly works. Now, if you back off to the Omega Centauri cluster, turned around and looked at the sun and did this, same thing, same image, looking at the sun, same distance, there would be 6 stars in the image. Here there are 50,000. So this gives you a clue to how densely packed the core of the globular clusters actually are. They're so densely packed that sometimes stars actually do bash into each other. They have a special name for them. They're called blue straggler stars. We'll worry about why they call them that later, but it does happen occasionally. So if we go on. Now we have little open clusters, we have big globular clusters, and then we just have clouds of stars. So here you can see the color gradient. There are a lot of blue stars. There are a lot of sort of yellow reddish stars. They are separated from each other, and there are dark lanes, which are dust that you can't see through, so you see only the stars on your side of the dust. And there is a veneer, which you see best here, of very small blue stars, the foreground stars. So these blue stars cover the whole image in the foreground, and then way back in the background, there are a lot more blue and yellow stars. And we can put some labels on this. There we go. So these little red spots, these are emission nebula, hydrogen 2, H2 regions. This one I think is called the Butterfly Nebula. There's the North American Nebula. You can see why it's called the North American Nebula. And I'm not sure if I thought this might be the California Nebula, but I don't know for sure. But I mentioned it because the Los Angeles Astronomical Society has sneakily tried to get the California Nebula declared the official nebula of the state of California through the state legislature. And we haven't really hit a happy spot with them yet. That it gets delayed because more important things come up in the legislative calendar. I can't make it one. But at some point, I hope we will have a resolution declaring the California Nebula to be California's official nebula. And so these stars are towards the central region of the galaxy. You can see there's Vega, Deneb, and Altair is down here somewhere out of the image. So remember this gradient of going from blue to yellow stars. These are smaller, lower mass, cooler stars than these. And we'll see that in this image of the Andromeda Galaxy M31. Here's the same gradient, the blue stars out here, the yellow stars in the middle as you go, say, from the left side towards the center of the galaxy. So if we are out here in these blue stars looking that way, we're going to see blue and then red and the foreground stars. So here you can see what we saw from inside our own galaxy. You can see it now in the structure of M31, which is about the same size as the Milky Way. There's a constant tug of war going on between which galaxy is bigger, M31 or the Milky Way. And every couple of years, somebody publishes a paper that says M31 is bigger, Milky Way is bigger, M31 is bigger, Milky Way is bigger. They're about the same size, who knows? And they dominate the local group of about 100 galaxies. All the rest of them are no more than 2 or 3% the size in mass of the Milky Way. And so the Milky Way and M31 completely dominate the local group of galaxies. There's M110 and M32. But they're actually, M32 especially, is actually a nice object in the 60-inch telescope. If you get a chance to go to Mount Wilson, if you rate something like that again this year, and Andromeda's up, M32 is actually a nice object to look at. So this is the closest of the really big galaxies, about 2.5 million light years away. So galaxies evolve because of the stars in them. The stars evolve, and that forced the galaxy to evolve. What I've shown you so far are ordinary stars, not average, but ordinary. And the sun is an ordinary star, even though it's a very big ordinary star. These are not ordinary stars. This is Eta Carina, a southern hemisphere object, which in 1843 blew up, and everybody thought it was a supernova. We now call it a supernova imposter event because it got very bright. It got up to about -0.8 magnitude. It was the second brightest star in the sky next to Sirius. But probably we have a binary, a 100 solar mass luminous blue variable and a roughly 30, 40 solar mass Wolf-Rayet star in a binary system. And the Wolf-Rayet star probably had a hiccup and blew off this cloud of expanding dust. And if you look at this with the Hubble Space Telescope, come back and look at it next year, and next year you can see it getting bigger. You watch the expansion of so the glass is moving very fast. So Wolf-Rayet stars, here is an example of a Wolf-Rayet star, are so hot at the surface, many tens of thousands of degrees, 40, 50,000 degrees, that they are literally, the pressure of the star light blows away the outer layers of the star. It's too bright to hold together. Remember, I was talking about the sun being in equilibrium. The outer radiation, the radiation from the inside pushes out, gravity pulls in, it's equilibrium. In this case, the radiation completely overpowers the gravity and blows the star apart because it's way too hot. When it cools down, it will reach equilibrium. But for the time being, it's too hot, blows away the outer layers of the star, and they form this nebula. And so this star, which is WR124, probably began as a 25 solar mass star and now has around 9 or 10 solar masses. So there's a good 15 solar masses of stuff in this cloud. And the solar wind, that wind I talked about that comes out from the sun and hits the earth, maybe 5 to 10 protons per cubic centimeter where the earth is. The wind from these stars anywhere from 1 billion to 1 trillion times denser. So this is a series. If you were on a planet around this star, you wouldn't be on the planet around that star because it would suck you in and kill you. That would be the end of it. And some stars rotate back. Can we go back?
I just want to know why it looks like a dumbbell.
Oh, this, yeah. It's it's a binary system. So apparently what happens is in the plane of the orbit of the two stars, there is like a debris disk, which prevents stuff from getting out that way. And it comes out as a dumbbell or hourglass shape. And we'll see this again later on. This is a theme in the formation of planetary nebula, which I'll show later. But that is apparently what's happening. Feel free to interrupt me with questions if you want to. Okay, now let's go on. So, and some stars are extraordinary because they spin very fast. So the Earth takes 24 hours to go around once. It's very lazy. The sun takes maybe 25 days to go around the equator, and a little bit longer than that, close to 30 days at the poles. This is Regulus, which is in fact that much bigger than the sun. That's the sun. This is Regulus in a realistic comparison in size. But Regulus takes 16 hours to go around once. So it's moving really, really fast. So fast that it's squished in, squashed out. It looks like a disc that's spread out this way and squeezed in at the poles. The disc that in cross section looks like this. Our theory for rapidly rotating stars tells us that the poles should be brighter than the equator. And that's what we see in this data from the optical interferometer of the Center for High Angular Resolution Astronomy at Georgia State University, the CHARA array, which is at Mount Wilson Observatory and is the largest astronomical optical interferometer in the business, and is about to get larger because they already have one new telescope that they're working on characterizing and adding to the array now, which will make it 3 times bigger than it is. Yes, ma'am. The poles are here and the equator is here. So the spin axis of the star is horizontal across this image. We're seeing it edge on and tilt. And because this data has been kind of smoothed up and cleaned up in order to look good, because this image comes from a web page that is published to the world. And the one thing you will never see on a web page published to the world is an image the way it looks when it comes out of the space telescope, because they look like crap. They look horrifying. You have no idea what you're looking at. Then somebody takes 10,000 of them and adds them together and cleans them up and makes something like this. When we publish a paper with something like this in it, the images do not look this good because we're interested in doing science and not public web pages. So you have to be careful when you look at any web page, NASA web page, when they show you a picture from the Hubble Space Telescope, James Webb Space, they don't look like that. But they've been cleaned up for you. And the captions you read are not always the captions they got from the astronomer they asked the caption, because we can't say it that way. We have to just diddle the words a little bit. So there you are. So how big is big anyway? So here you've got the planets, Mercury, Mars, Jupiter, Venus, and the Earth, arranged in order of size. And so we're from the biggest of the little planets. So in each panel, the first object is the last object from the previous panel. So there's the big planets, Neptune, Uranus, Saturn, Jupiter. Jupiter is the first thing here. This is a roughly Proxima Centauri, which is the closest star to our solar system. It's part of the Alpha Centauri triplet. You see, it's not a whole lot bigger than Jupiter in physical size. And here's the sun, which is bigger than 95% of all the stars around. So the vast majority of stars in size are between Proxima Centauri and the Earth. But there are bigger stars, and their number count drops off rapidly as you get bigger. So when you start talking about stars like this, very few of them in the galaxy. This is Sirius, that's Sirius. Pollux, Arcturus, and Aldebaran are classical red giant stars. The sun will become something like Aldebaran at some point. And here's Aldebaran here. This is Rigel, the blue supergiant star in Orion. That's down in the lower right corner as you look at it from the northern hemisphere. This is Betelgeuse. Betelgeuse is maniacally difficult to get a distance to Betelgeuse. It's a terribly hard problem. There's constant flow of papers of people trying to figure it out. But it's roughly 4.6 astronomical units in radius, which means if you put it where the sun is, its outer edge, its photosphere would be a little short of the orbit of Jupiter around the sun, which is around 5 AU. So it's almost as big as the orbit of Jupiter. It's big, but it's not the biggest. So there's Betelgeuse and a couple of other stars, and every couple of months somebody finds a star that's bigger than the previous star. So the current record holder for linear size, largest star, is WHOG 64 in the Large Magellanic Cloud, which turns out we can actually figure out how big it is fairly easily. It has a radius of 7.16 AU, and by comparison, I'm showing the aphelion distance, which means the farthest you're going to get for Jupiter is nearly 5.5 AU, and the perihelion distance for Saturn is just over 9, and about halfway between them, you're going to find the surface of this star. So if you put this star where the sun is, Mercury, Venus, Earth, Mars, and Jupiter are all inside the star, and Saturn is just kind of skirting around outside the star by a few AU. So they can get very big in size. Stars can get a lot bigger than the sun. So the assumption of the sun being an average or relatively small star comes from the realization that when you go out at night and you look at it, the darkest sky you can get. So what, 2,000 or 3,000 stars on a really dark night? Every single one of them is bigger and brighter than the sun. You cannot see the sun from that distance. And so once astronomers realized that, without realizing how many small stars there are, they figured, okay, well, the sun must be pretty wimpy because all we ever see is bigger stars than the sun. And once they got bigger telescopes and started looking and seeing smaller and smaller and smaller stars, they came to the realization that, okay, the sun really isn't all that small after all. We just couldn't see. So that's why people talk about the sun being an average star. So,
Well, Tim,
yeah.
I'm just wondering, in that picture there, the B sub S, is that the volume of the sun?
Yes.
Okay.
And so this is 3,652,000,000 suns would fit in this if it were a bag. That's not quite correct. The volume of this is that much bigger than the volume of the sun. But then you have to start, it's a mathematical problem how you pack spheres. And so you wouldn't be able to pack quite that many spheres into this spheres because there's empty space between the spheres. So you have to start doing modeling equations for how you pack the spheres, and the people who do molecular chemistry like worry about that, but I don't. So that's about it. Yeah. Okay. So color and brightness. Let's just talk about that for a minute. Go ahead. Big deal number 3. Astronomy is the ultimate remote sensing science. I worked on a geological infrared remote sensing project, and what we would do is go out into the desert, a place called Railroad Valley in Nevada, which actually is in the middle of nowhere. If you want to be in the middle of nowhere, go to Railroad Valley, Nevada, and you'll be there. It's a dry lake playa that's miles across. You go out there in midsummer, it's hot, there's no shade, there's nothing except crawling under your truck if you want to be out of the sun. And we would stare at the ground. The satellite would go over, look at the ground. Satellite would tell us what it thinks the ground looks like. We would see what the ground really looks like, and then we look at the difference between them. And if the difference is not important, that's good. If the difference is big, that's bad. And so since I wrote the software that tells the satellite how to decide what the ground looks like, I was very interested in the results. And they actually turned out to be ridiculously and unexplainably accurate. I have no idea how I was ever able to produce results that good with the method that I used, but I will take credit for it anyway because it worked. Impossible to explain. But the point is, you can go there and do that. But you can't go to any of the other stars. You can't go to, we can go to the moon and the planets, and that's about it. But all these stars, you can't go there and see if you got there, go, you get scoop of it and put it in, yeah, it looks like it. So we just have to hope that we got it right from whatever light we get. That's all we get is the light that comes from the star. So, next. So here you see color and brightness. Red, blue, red stars, blue stars, white stars. This is a Hubble Space Telescope picture. Looking in, I think, Bode's window. Yes, this is a very peculiar view. If you look through Bode's window, you can see from here all the way through the entire Milky Way out into intergalactic space on the other side, and actually see the undisturbed cosmic microwave background. Very peculiar. But here you see there are lots of brightness and colors. We assume that these stars are dim because they're farther away, but maybe they're nearby and they're just tiny. If you look at a picture like this, you don't know the difference. You can't look at this picture and say, this one is nearby and tiny, this one is very far away and big. You can't do that. So you have to do something else to figure out what's going on around here. Let's see the next one. And so when you look at the colors of the star, we're used to on Earth, blue is a nice, cool color because it's ice and water, and red is the hot lava. But when we look at stars, it's exactly the opposite, as we will see. The red stars are actually the cooler ones, and the blue stars are the hotter ones. Here, the temperature is given in degrees Fahrenheit. I've added it in degrees Kelvin for those of you who like Kelvin. The sun is about 5,800 kelvins at the surface and a lot hotter inside. So as you can see, the sun is pretty far up. It's pretty low down. But so the bigger stars that are a lot hotter than the sun, number very small. So let's take another look. This is what's called the Hertzsprung-Russell diagram that first began to be invented around 1913. And you would think if you plotted color versus brightness, it would be random. Why can't a star have any color and brightness that it wants? Color we define by the difference between two defined filters, because color doesn't exist in nature. Your brain and your eyeball make it up. So when I tell little kids that the sky is not blue because color doesn't exist, they're like, what? What do you mean color doesn't exist? So it's a good education. Think about it if you haven't before. So that's how we define color. Brightness is easy. You can tell by looking at something, bright, dim. And this is what it looks like when we take 23,000 stars and make 23,000 dots and compare brightness and color. It is exceptionally not random. So the sun is right about here. The vast majority of stars are down in the red end of the main sequence. They call this the main sequence because most of the stars on this plot are along that line. This very small number of stars up here in the giant area, very small number down here in the white dwarf area. Most stars are up in here. The sun is a main sequence star. This is a product of stellar evolution, and I'll mention that again in a few minutes why it looks that way. But for the time being, it's just worth remembering that stars cannot have just any color and brightness. No star exists, and no star can exist in this region of the diagram. There are none. And if you find one, and sometimes astronomers do, they say, hey, I found an impossible star right here. You look closer and it's a binary. It's one of these and one of these, and it fools you, thinking you're seeing a star, but it's actually not. It's a binary. So let's move on. So let's talk about spectroscopy for a minute. This is the way people used to do spectra. You'd photograph it, and you get something that looks like this. This is the way digital instruments all do it now. But you can see the rainbow. If you're looking at the sun, and that's what this is, the solar spectrum. So that rainbow of light is light generated way down deep inside the sun. As it passes through the photosphere, some of this light is sucked up and redistributed by various elements. This is a carbon-hydrogen radical. Ionized calcium, hydrogen, beta, hydrogen alpha is out here, neutral magnesium. This is terrestrial O2, remember that you're looking through the Earth's atmosphere. If you see that line and declare I had discovered molecular oxygen on the sun, which is thoroughly impossible, everybody's going to laugh at you and tell you actually, no, you discovered oxygen in the Earth's atmosphere, which is good because we breathe it, right? It's very handy. So you have to tell the difference between lines, absorption lines in the star and absorption lines in the atmosphere. But this spectrum includes all kinds of information you can derive from this, what element you're looking at, how much of what element you're looking at. You can get the temperature, the pressure, the density, magnetic field, all kinds, what direction is it going in? Is it going this way? Is it going that way? You can get a whole lot of information is encoded in here. And this is the backbone science of astrophysics. If you can't do spectroscopy, you really just can't do astrophysics. So this is huge. And so we can classify stars. Here are examples of the spectrum and the star type. The sun is a G-class star. This method of doing things was originated by Angelo Seppi, who was a Jesuit priest in Rome. And then it came to Antonia Mari. Yes, her uncle, as it turns out, was a close friend of Angelo Seppi, and that was just coincidence. Angela Mari was one of the famous, Antonia Mari was one of the famous Harvard computers, all of whom were women and are worthy of a talk of their own, and accomplished some of the greatest accomplishments in astronomy and astrophysics. Antonia worked on it, and Williamina Fleming worked on it for a while. Annie Cannon is the one who finally completed everything in 1901, invented this method for classifying stars. And Annie Cannon would use a small magnifying glass and look at a very tiny spectrum like this, and she would classify 3 stars per minute with that glass and did 500,000 stars minimum herself just by doing that. And nobody will ever do that again because computers do that kind of stuff now. So we can classify stars by their spectrum. So if we look at the spectrum and see this, we know what its temperature is. We know what lines to expect. And for magnetic fields, if you have one spectral line, it will split into 3. So here, this is an image of the sun. And this is the slit of a spectrometer. And in this image, this direction, vertical direction, is vertical along this line. So you're moving spatially up the image. But this direction is wavelength. This is not physical space here. It's wavelength. So high frequency, low frequency. These are iron lines. One spectral line converts into 3 in the presence of a magnetic field. This was discovered by Peter Zeeman, who was fired for making this discovery because he wasn't doing with the laboratory equipment that which his boss told him to do. Then he was given the 1902 Nobel Prize in Physics for discovering it. As far as I know, he did not do what I would have done, which is take that Nobel Prize back to the guy who fired me and say, I was working in your lab. Your name could have been on this, but it isn't. It's all mine. Thank you. And so there's Albert, there's Peter Zeeman here, and this is Aaron Fest. And every talk has to have a picture of Albert Einstein in it, right? Because you can't do that without Albert. And if you like quantum mechanics, why there's an explanation for why it works this way. You probably don't like quantum mechanics because nobody does. So we can switch to the next slide and talk a little bit about stellar evolution before I bore you completely. This on the right is a diagram that explains what I was talking about before, the star collapsing under the force of gravity. As it collapses, it flattens out and spins faster because of conservation of angular momentum, forms an accretion disk and then a debris disk as the planetary systems form. This is a generic picture of how we think stars form. I actually was going to go looking for a better one, but I didn't have time to do that before this talk, so you're stuck with the old diagram. However, we see pictures from the Hubble Space Telescope that look a lot like what we see in the diagram, and these are all from around the Great Nebula in Orion. And so it looks like that is indeed what's happening, and there are hamburgers in space, as you can see. And so now remember this diagram. I showed this to you before. So each one of these dots represents a star, but stars change with time. So if you come back in 1,000,000 years and do this exercise again with exactly the same star, these dots will all move to some other place. Then in another 1,000,000 years, the dot will move again. And it will move again because its stars changing and evolving with time. So if you do that a whole bunch of times, you can play connect the dots. And you can watch the sun become a red giant and there's some tiny giant branch, and then it become a white dwarf and planetary nebula. And so when we look at the next slide, we will see that. Here you are. You're playing connect the dots. That's the sun now. We know it used to be a T-Tauri's type variable star before it became a main sequence star. 10 million years ago, it was cooler and dimmer than it is now. And it's been working its way up, getting hotter and brighter. And this introduces what's called the faint young sun paradox in the paleontology of the Earth, because we know the Earth used to be a lot hotter than it is now, but the sun was a lot cooler than it is now. How does that happen? It's the atmosphere of the Earth, not the sun, that's doing it. And eventually, in a few billion years, the sun will become a red giant. It will reach this way up here, become a red giant star. You'll start fusing helium in the core. I didn't talk about that before because you don't want to be here all night talking about nuclear physics. And then it will shrink and brighten up and become a horizontal branch star. Then it will go become a red giant. And finally become a planetary nebula. And our sun will eventually be a white dwarf star down in the lower left corner of the HR diagram, with maybe half of the mass that it currently has. And the other half of the mass will become one of these things, a planetary nebula. The reason they're called planetary nebula is best exemplified with this one, because in old telescopes in Herschel's day, they looked round and fuzzy. So they're fuzzy like a nebula and they're round like a planet. Therefore, they are a planetary nebula. It has nothing to do with planets. Then you get the Hubble Space Telescope and you find these things and these things. And what's round about that? And the answer is nothing. And so if Herschel was looking at one of these, he would not be able to get this kind of detail. So we call them planetary nebula because astronomers never change what they're doing. I like this one because you can see a distant galaxy through the planetary nebula. This one and this one have that same hourglass shape that the Eta Carina Nebula had that you asked about. And in both cases, there is a disk of material here, kind of like the disk of interplanetary dust in our own solar system, that prevents expansion in this way and sends stuff out this way. And the central star is rotating, and so there are jets of stuff sticking out. And this is the Ant Nebula. And when my late wife was a school teacher, her students told her this was the eye of God looking back at them from the universe. So if you like that reference, cool. This is the Cat's Eye Nebula, which kind of looks like a cat's eye, but there are multiple axes of symmetry here as the interior star is rotating. And we get more and more. The better our telescopes get, the more detail we get, and the harder it is to explain where all this detail came from. Sometimes it's too much information. You like to have a fuzzier image so you don't have so much to explain. And the Helix Nebula up here, they're all a few hundred to 1,000 light years away. This is what will happen to the sun, something like this. But more massive stars, and we'll take a look at that, more massive stars do something different. The sun is fusing hydrogen into helium. It will eventually fuse helium into carbon and oxygen, and that's it. We'll quit. Won't go any farther. It'll become a planetary nebula, white dwarf star. But more massive stars start fusing heavier elements. And here is like Betelgeuse, for instance, will look like this inside. It's a little bit smaller than Jupiter's orbit. This blue bar is the diameter of the Earth by comparison to this diagram. So this thing is roughly the size of the Earth at the core of a star, the size of the orbit of Jupiter and our planet in our solar system. And this is where all the nuclear fusion is going on. You're getting on the outer shell, hydrogen is fusing into helium. The helium is raining down into this shell where helium is fusing into carbon, which rains down into the shell where carbon fuses into neon and heavier elements, oxygen fuses into silicon, silicon fuses. Eventually you wind up with iron. You can't go any farther when you get to iron. It just sits there. then it gets hotter and hotter and hotter and hotter, and eventually the heat causes the iron nuclei to tear apart and become helium nuclei. That means there's no longer any bound atoms in them. There's no longer any physical structure. And this little core here, is somewhat smaller than the size of the Earth, almost instantaneously collapses into something very, very tiny, a neutron star or a black hole, and the whole star collapses in on it, and you get a supernova explosion, kaboom, really super. And so here is the Crab Nebula supernova 1054 on old style Julian calendar they used at the time. It would have been the 4th of July. Unfortunately, we don't use that calendar anymore. On our calendar, it would be the 10th of July. We can actually see this gas expanding towards us. If you look at it with the Hubble Space Telescope, James Webb Space Telescope, look at it, come back, look at it a while later, come back a while later. These things have all moved and expanded. You could do a Doppler shift on them and see what their velocity is. Anyway, so there's the expansion velocity, 1,500 kilometers per second, about 0.0067 light years per year, 3 million miles per hour, which sounds a lot more impressive to me. There's the only optical pulsar I know of is in here, which pulses on and off and rotates 30 times a second. So something about the size of Los Angeles County with the mass of the sun spinning 30 times a second. It's quite a fantastic thing. And for those of you who really, really like conspiracy theories, I will point out that within a week, about 10 days after this supernova blew up, the Bishop of Rome, whom we call the Pope, excommunicated the Bishop of Constantinople, who returned the favor and excommunicated the Bishop of Rome a few days later. And that is the birth of the Great Schism, which is the split between Eastern and Western Orthodox Christianity. And you can figure out for yourself if this was an omen of things to come. And is there a secret code embedded in the Crab Nebula that will explain when the Eastern and Western Orthodox churches will come together again? I don't know, but I just thought I would mention that in case any of you are curious about it. And with that conspiratorial note, I'm done. So thank you. And I'll be happy to entertain any questions.
I can see the
Well, you can see a lot of things.
Yeah, could you go back to the slide where those the diagrams that depict the formation of the planets? Up in the upper right-hand corner.
This
Right there.
one? Yeah.
This phenomenon where you have a planetary disk along with outflows that are perpendicular to it.
Yeah.
Is very interesting. It's something very similar to what you see with the black holes.
That's right. And you see this ubiquitously. It's everywhere.
Yeah.
And the reason you see it is that the magnetic field of the central star, you remember the loops of magnetic field on the surface of the sun. The magnetic field loops out of the star and connects to the disk. And there's an electric circuit there. There's a current flow along that. And so the magnetic field aligns when you try to push gas out, it can't go against the field. It rides along the magnetic field lines and rides up the pole to fly out. So you see this in a black hole accretion disk, you see it in planet formation, star formation, and you see it in active galactic nuclei where you have a supermassive black hole sucking up lots of stellar material. Same thing. This is a ubiquitous structure throughout astrophysics, and it's caused by the magnetic field focusing the plasma beam in that direction, always along the magnetic axis, not the spin axis. And so if the magnetic axis is offset from the spin axis, then it will rotate like one of those, garden sprinklers. It won't rotate straight. And that's what causes pulsars to pulse, because if we're looking at the pulsar and its magnetic pole comes along to our line of sight, we will see it pulse. And if it doesn't, we won't see a pulse. So it's probable that every neutron star is a pulsar. We just can't see it because its pulse is going somewhere else.
So when you look at the images from Hubble of those places where there's a planetary,
Yeah.
you know, planetary systems being formed, you can automatically tell, just looking at the picture, the orientation of the magnetic field.
That's right. This is going to be along the poles of the magnetic field.
Interesting.
If you look at these images on the sky, they're undoubtedly going to be randomly oriented. If you look at them on a web page, they will be oriented so that they look good.
Now, I noticed that the one over here in the upper left looks like it's perpendicular to the planetary disk. I
Yeah,
assume that there are others that are not.
I'm sure there are. I just haven't seen any
Yeah.
lately, but yeah. Here you're getting flare. This is light. This brightness is light reflected from the central star off the dust disk. So you can't see the star directly, but you're seeing light reflected to you.
I want to ask about our sun, the rotation that you,
The differential
the
rotation.
differential
Yeah.
rotation that you see in which would be the photons.
Yeah.
Right.
Yeah.
Is that a remnant of the motion of the completion disk?
It is. Everything in the universe rotates. And so people have asked, why does everything always rotate? And it's, because during the formation process, it shrinks and conservation of angular momentum forces things to spin faster. That is, the rotation of the star is a leftover effect of its formation. The differential rotation is a little different than that, and it's because of the convection. So now you have two motions. You have the convective motion this way, and it's rotating this way at the same time. So like a torque, basically, and it's greatest at the equator, so that it rotates faster at the equator than it does at the pole. But when you get to the base of the convection zone and look at the radiative zone inside the star, it does not rotate differentially. It rotates like a solid body. So there is a difference at the point where they meet, which is called the tachocline. Out here, you get differential rotation. Here, you do not. So there's a friction there. And the assumption is that that's where the magnetic field of the sun is generated by a dynamo process, because you now have this discontinuity in the rotation. Some recent observations have begun to question whether or not there is a source of magnetic field higher up in the sun, and that would be problematical to explain. So we'll see if those explanations work out at the end. But for the planets, like for Uranus, Neptune, Jupiter, is virtually certain that the source of their magnetic fields is high up in the planet, not deep in the core, because they're too asymmetric.
The one, for you here, Tim, talking about, magnetic fields. You know, the solar cycle, they always refer to as 11 years, actually it's 22. I
That's
guess,
right.
Because of the flipping of the field. And it's not just the sun, it's also the earth. Earth
Yes.
has a magnetic field that flips periodically too. And the last time that has happened on Earth is a long time ago, not longer than most of the times that it flipped. And
That's
there are
right.
signs right now that the Earth's magnetic field is getting ready to do that. Is there any concern by the astronomers of something like that happening soon?
Whether or not the Earth's magnetic field is getting ready to reverse or not is open to serious question. But if it does, I don't like the word flip, begging your pardon, but flip makes you think this. What actually happens is that the dipole field collapses entirely and becomes a multipole field with lots and lots of structure. And then it reforms with its magnetic poles reversed. That's what the sun does. You can see it doing that. During the sunspot maximum, when there are lots of spots, that's when the sun's field has collapsed and is now multipolar. And you see that in the sunspot structure. Then when it comes back, the sunspots go away. The sun's magnetic field is relatively periodic. Roughly every 11 years, it reverses itself. So it's half of a 22-year-old field cycle. The Earth's magnetic field reversals are absolutely not periodic. They're completely random, completely stochastic. Nobody can predict when it will happen. Nobody really knows why either one of them happened. That's something plasma physicists are still spinning their heads around because they just don't know why it does that, but it does. And the Earth's field will do the same thing. And so what we're seeing is that the dipolar component of the field is getting weaker. That could mean that it's going to do this. It could also mean it's just getting weaker because some funny thing is happening down there and then it's going to come back. And we've seen that happen before too. We have seen the field go down there, come back up without reversing. So you just don't know what's going to happen. However, if it does collapse, then the magnetic field as a shield against cosmic rays and the solar wind goes away. And the solar wind can impinge directly on the outer atmosphere of the Earth. That will probably generate a lot of ultraviolet and X-ray, other bad stuff, so that life on the surface of the Earth will probably become a lot more difficult. Who knows? Maybe we'd have to bury ourselves in caves or something and become cave people again. But yeah, they will. But don't worry about it because, 3.5, 4 billion years, the sun will gobble up the Earth and be gone anyway. So let's do it.
That's so much better.
You're welcome.
Well, as long as we continue to navigate by GPS instead of using a compass, it should be no big deal.
Yeah. If your GPS satellites survive the collapse of the magnetic field. Is there anybody on Zoom with a question? Is there a way to find out? I don't want to ignore them all. Like the Zoomies don't exist. How many Zoomies are there?
Well, about half of them left when you said you were done.
Oh, they give up too easy.
They got scared.
Ron, you had a question?
Oh, yeah, I can't remember how to pronounce it, but Ada Karina,
Ada Karina, yeah.
Karina. Okay. You said there's two stars, one about 100 solar masses
Yes.
and one 25.
Yeah, 30 or so. Who
30,
knows?
okay,
Yeah,
and
25, 30.
the smaller one is a Wolf-Rayet star.
Yeah, that's right.
Why would the smaller one be so hot on the surface and the bigger one apparently not be as hot,
The bigger one
the more massive one?
is, red giant stars are much bigger than the sun, but they're also much cooler. But they're much brighter because of the surface area. So the Wolf-Rayet star is probably not much bigger than the luminous blue variable, which is going to be smaller, very much brighter and hotter, and doesn't have the same kind of instability as the Wolf-Rayet star does. Because Wolf-Rayet stars only have that radiative instability for a short period of time. The bigger stars, the more massive stars, have enough gravity to overcome the effect of the radiation pushing out because it's 100 solar masses. It's a lot of gravity. Whereas if you're only 20 solar masses, you're a wind, right? And so you just blow everything away. But at those masses, extreme stars just don't behave the way you think they should. And stellar astrophysicists puzzle about that. I mean, there should not be a star that's 100 solar masses. That should be impossible. It apparently is not impossible because we can see stars that look like they're 100 solar masses. It's pretty hard to argue that something you see is impossible. You can try it, but it doesn't go over in most audiences. And so you have to find a way to explain it. And that's what we're working on now. How do we explain why those stars are so massive and do what they do?
On this main sequence that's being shown here,
Mhm.
and it shows each dot represents a star that they point. It says from the
Yeah.
22,000.
That's right.
Would you say that the bottom red down here might be a little undercounted just because they're so dim?
Yes, and that's a valid point. This is probably in general, this is undercounted. And that's why you will also hear it said, and I might as well correct this while I'm thinking about it, that most stars are binary. And that also is not true. It's probably pretty close to a 50-50 split, maybe most singular, not binary. And the reason is Helmut App during the 50s and 60s was looking at brighter stars. Larger, brighter stars tend to form in multiple star systems. Lower mass stars tend not to. They tend to form individually. But if you can't see this part of the main sequence, you only see this part, you're going to overcount the binary stars. And then once our telescopes get bigger and better, and we can start to see these stars, you realize, oh, there's more single stars, but nobody's bothered to correct that. If you look carefully through the literature, you'll find papers talking about this, but they're well hidden and nobody talks about them because they're lazy, right? And so they'll just keep telling you most stars are binary, and that's probably not true. It's probably about a 50-50.
Well, in this diagram, though, this is just a, what's the word, arbitrary.
That's right. It's an arbitrary selection of 22,000 stars from the Hipparcos catalog and 1,000 from the least catalog. You can make a diagram like this with a lot more stars. You could, if you wanted to do the exercise, you look through data like the Palomar Sky Survey or something. There are approximately just under 1 billion stars in the optical Palomar Sky Survey. And there's more than that in most of these catalogs now. You find easily 1 billion stars. And Gaia, which has really good distances, clearly has over 1 billion stars. And you could plot 1 billion dots, and then you really figure it out. But yes, as you, generally speaking, as you go from bright to dim, you're undercounting as you go further down because it's harder and harder to see the dim stars. You've got to be sure you've got the right equipment, know the limitations of your observation. In fact, there's a name for it, and I think that's what the Malmquist bias is, Malmquist. That's a bias that favors brighter objects.
Right. Like when I was in elementary school, they said, well, the Milky Way has 100 billion stars. And then when I was in high school, they said, well, the Milky Way has 200 billion stars. Then when I was in college, they said, well, the Milky Way has 400 billion stars. And I read an article the other day and it says the Milky Way has approximately 800 billion stars. And they go, and he goes, why do we keep changing it? And he goes, red dwarfs are actually pretty hard to see. It's sort of saying, why don't we count all the asteroids even in our solar system? He goes, because an asteroid, even a big piece of charcoal, is hard to see.
Yeah. Well, right now, if you look it up, Saturn has, I think, 142 moons. So somewhere along the line, somebody's going to have to decide what's a rock and what's a moon, because they're getting pretty small.
Yeah.
And so what qualifies, if I jump out there in my spacesuit and spend the rest of eternity in a heroic pose orbiting Saturn, am I a satellite that I get in the catalog? Am I going to be Saturn satellite number 560? I don't know. No, where do you draw the line? The same thing. I think 800 billion is a bit of an overcount, but 400 billion makes sense to me, and it's just guess. Nobody can count the stars, but we are pretty sure that the baryonic matter is outweighed about 10 to 1 by the dark matter. And the baryonic matter is going to be mostly, but not entirely, stars. Part of that mass is going to be dust and gas. You got to account for that.
Mm-hmm.
And so what they do, like when you look at a James Webb Space Telescope picture, they tell you this galaxy 13 billion light years away has a mass of so-and-so. The first question is asked is, how the hell do they know that? And what they do is they have a population of stars. They assume this many of these stars, this many of those stars, this many of these stars, this many of those stars, figure out how bright that would be, and then look at the galaxy and say, it's this bright, it's that bright, it must be these stars, it must have that kind of mass. Well, you can play around with that and create a whole bunch of different stellar populations to give you the same brightness. You don't know which one is the right one, but one of them has a lower mass than the other one, and so they could easily have the mass off. And there are several papers now arguing that that's exactly the problem, because we're discovering what appear to be very massive galaxies very early in the universe, seen with the James Webb Space Telescope, but we could be overestimating the mass. And if they're not that massive, then they're less surprising, which makes cosmologists more comfortable because it means they're not quite as stupid about galaxy formation as they thought they were. So we'll see.
So as
Yep.
you go off the bottom right of the Hirschsprung-Russell diagram, you're getting into the smallest red star, dwarf stars.
Yeah,
At some point, you are going to grade into the biggest brown dwarf.
that's right.
And we're probably just now getting the ability to detect more brown dwarfs because they're effectively
Yeah.
exoplanets.
That's right.
So do you have a guess or an expectation? Does anybody know, like, on the boundary between being a star or a brown dwarf, do we know if there are processes that would push things one way or another? Like, do we expect that to be a continuum from stars into brown dwarfs, or do we expect there to be bumpy, the distribution?
I don't think anybody knows. I would guess that the distribution would be continuous. It certainly is throughout the stellar portion of the diagram. And I'm not familiar with HR diagrams that show the transition from stars to brown dwarfs. But there will undoubtedly be a lot of objects that you can't tell. Is it a brown dwarf or a star? Because if we presume wrongly, over precisely, that exactly 80 Jupiter masses gives you a star, and below that gives you a brown dwarf. If you've got 79.8 Jupiter masses, well, okay, are you really a brown dwarf, or are you really you can't tell without looking very carefully to see if you can see hints of the evidence for nuclear fusion. And the only star we can do that with really is the sun, because we can study solar neutrinos, which we know are generated by the nuclear reaction to the sun. We know the energy spectrum of neutrinos that will be generated by the sun. So we can look at those neutrinos and tell exactly what kind of fusion is going on inside the sun. But we can't see the neutrinos from any other star. So we don't have that ability for some random red dwarf star out there somewhere. No. So there you are. You're just always going to have this question.
Do we expect brown dwarfs to evolve at all, or do they just sit there cooking deuterium?
They will probably not evolve the way stars do. They will just sit there like white dwarfs. White dwarfs are done evolving. They will sit there and cool and cool and cool and cool and eventually become black dwarfs. The problem is the universe is not old enough yet for a white dwarf to cool. So one way you can get the age of a globular cluster is to get a diagram like this and then look at the distribution of white dwarfs. And if your sensitivity and brightness goes down far enough, you will see a hard bottom to the distribution of white dwarfs. And that will tell you it's not old enough for those to cool yet. And that will give you a sense of the age. And you can say, how long does it take white dwarfs to cool that far? And you can compare that to the red giant turnoff edge, because with the globular cluster, you would look at this diagram and there would be none of these stars would be that all gone. They've all evolved into red giant stars. So this point right here, which is called the turnoff point, tells you the age of the cluster. And that's how they get the age. So if you do this and you do this and you get the same age, you have reason to believe you know what you're talking about. Otherwise, you might not.
That's cool. I didn't realize there were two ways to get there. That's neat.
Yeah. Bamboozled.
Right. Thank you, Tim.
Oh, yes.
If anybody wants to help Jim Thompson not have to carry so many cookies out of here, you always do the right thing.
Yeah, eat them all.